DigiPen. We're a small four-year private college just down in Redmond. We have our 8 undergraduate programs ranging from more scientific, like computer science, to more artistic, like the Bachelor of Fine Arts. All of our programs revolve around developing for the video game industry. We're well known. We're actually the first college to offer a program designed for game programming. All of our students are working on game teams, creating video games, all 4 years at DigiPen, and go on to workplaces like Microsoft, Bungie, Valve, and the like.
Wendy Bartholomew, Air Washington at Skagit Valley College, and we teach a composite program at the Marine Tech Center in Anacortes. One of the programs that we do is we make materials out of composites. This is made out of carbon fiber, and the very edge you can see the fiber. Well, this is layered together with different layers of carbon fiber, and it's vacuum sealed together. We call it a VIP or vacuum infusion process with some resin, and it makes a real hard product. And here's a complete version of it. The students can actually make skateboards in class. This one's made out of fiberglass and paddles. All of the molding and the tooling are also done by the students. One of our new programs that we're real excited about is our non-destructive testing. An easy way, an old-fashioned way of doing non-destructive testing is using a tap hammer, where you can tap materials in different areas, and it displays the density right here on the screen. And the numbers should be right about the same everywhere you tap, as long as you're applying the same pressure. If that number changes, that's where you know that there is a problem. A more advanced version of doing it is with the non-destructive testing ultrasound waves. This is not completely programmed, but you do have to use the gel to pour over the material, and then you run this over, and it's going to show on this graph. And then it also shows there's 4 different items that it's testing on. It's going to show height, width, depth, and density, and uses all 4 of those characteristics to find where and what type of flaw you're going to find them in materials.
The normal thing is people think forensics is its own science, and it's not. Essentially what we're doing is we're taking any science that's out there and using it to answer questions about crime scenes for a court of law. So you may be a biologist, and so then you would be looking for DNA on something and trying to figure out if the DNA that you found at the crime scene matches the DNA from a suspect. You may be a firearms person who really likes guns and taking apart guns. Well, then what you might be doing is looking at bullets to see if they came from the same gun, looking at bullets to try and identify a particular, if you may not know what gun it came from, but you have this bullet out at the scene, from the markings on it, you may be able to give the agency an idea of what kind of gun they should be looking for. You may be looking at bullet holes, try to determine where the shot came from. You may latent print people basically, or what they're doing is they're looking for invisible finger marks, try to enhance them, and then compare them to the standards to see if they're from the same people or not. Same with handwriting comparison. So you may, if you like looking at lots of handwriting, you can do handwriting comparison. So basically here we have, say, something at a scene, something that somebody wrote at a different time. Are they from the same person? Did the same writer make those? And then we have people that actually are just out at crime scenes collecting the evidence and packaging it. You don't have to be a scientist to do that. You probably have any kind of degree. You may be able to just do it with a high school degree. Most of these people work for a police agency of some sort. And also, not only do they work out at crime scenes, they probably handle the evidence for the police agency as well. And then one of the most common ones are computers. So So you may, if you're interested in computers, you can do computer forensics where you're looking at files and trying to determine were they deleted, who deleted them, when, that kind of thing. When was an email sent, who was it sent to, that kind of thing.
Like a certain
And your best leverage is holding back on the hammer, squaring up. Okay. You notice how it's chipping stuff out?
I should turn that one on. Because instead of, like, if there was a disease that knocked up all of one type of species in a forest, then these species would still be and we got to mix up with the one that's being affected by the disease. Oh, because it's different technology.
The whoosh bottle. Yeah. Whoosh. First we're going to demonstrate and then we'll say how it works.
Was that good? Was it good? Okay.
I got one. Remember, you gotta check out my photos. Yeah, it was second. Yeah, third.
Huh?
They can't do shit like that.
Yeah, we can.
No, you can't.
I said, yeah, we
Busy. Okay, here's one here.
So you can stick the wood into his hand, or
Ready? It floats. It's rough. Doesn't float. It's rough.
You were talking about one. I know the whole
Doesn't float. Am I making this video awesome? This rock is gonna float. Watch.
Mirror. Research telescopes use mirrors to gather light. And any of my astronomy students, Alyssa included, can tell you that the most important job of the telescope is, Alyssa, to capture light, exactly, to capture faint light. To do that, you need really big opening. Just imagine the size of how much light you could capture if your eyes were 2 feet across, like this thing. Well, Hubble's eyes aren't 2 feet across. Hubble's eyes are 8 feet across. In the heart of the Hubble is a mirror that's as big as the floor to this black ring that represents the horizon. It's an 8-foot dish mirror. It costs many millions of dollars to make. Turned out there was a problem with the mirror when they first launched the telescope, and then it turns out they fixed it. It's an amazing story. I'm going to show you some pictures from the Hubble in just a few minutes. Before we go there, though, we're going to look at the sky in Mount Vernon. So, go ahead, Alyssa. Let's pull that piece of paper down over the projector. I have to look and see in my program. The next one before I forget, with Josh. And the next one is supposed to be wow, science next line. Okay. So, this is daytime in Mount Vernon. Can you see the moon in the daytime? Sometimes you can. There's the moon right there. Okay? So, and there's the sun. So in the planetarium, we pretend that we're looking south when you're looking this way. Really, it's east, but just pretend. So that's south. What's the opposite of south over here? Okay, there's no name. There's some stuff on the carpet right down in front of you. Your eyes get used to that. No, so there's south. Just pretend like you're looking south. Well, then over here, this is east. What direction's opposite east over there? West. Okay, so, you know, when I turn on the motion of the Earth right now, here we go. All day long, so that's at about, 3:30, 4 o'clock. The sun's moving through the sky. And anybody who asks them, maybe they tell you, oh, the sun always sets in the west. Well, there's west. You can see it right over there. Or right here. That's west. So is the sun setting in the west? Well, no, wait. It missed west. West is down here. Instead, the sun's setting way up there. This time of year, the sun is setting up, heading towards the north. By the time we get to the end of the school year, it'll be in the northwest. And that means we get really nice long days. If you're like me and you like long days, this is the time of year that we like. Hey, as the sun goes down, the sky gets a little darker. And then you can start to see some other things. So over in the western sky, there's a really bright object. And that bright object has been hanging there for weeks. And when you look at it, you say, wow, it's a really bright star. But there's a way to know if it's a star or not. It has to do with a song that you probably all know. Is that a star? Well, the song goes like this. Twinkle, twinkle, little planet. Oh wait, planet. No, that's not it. Twinkle, twinkle, little star. That thing up there, it does not twinkle. It's a planet. So if you're wondering, like, well, first off, is it an airplane with its landing lights on? If it moves, well, yeah. But if it doesn't move and it's not twinkling, you're looking at Venus. Venus is super bright. This is the third brightest thing you can see in the sky on Earth. The sun is brightest, moon is second, and Venus, well, that's coming in at third. Something interesting about that light from Venus, Venus is so far away from us that it takes the light 9 minutes to travel through space before it gets to Earth. 9 minutes. That doesn't seem like very much time, right? That's a distance of about 100 million miles in 9 minutes. So traveling at 186,000 miles per second. There it is. Oh, from the moon, well, it only takes like 1.5 seconds to get to us. Astronomers would tell you that telescopes are time machines, and Hubble is like the ultimate time machine. We're going to look at some pictures in a moment through the eyes of Hubble, looking way back in time. First, what else can you see? Well, the sun's gone down, and then there's more things that appear. Another thing that's not twinkling, and that's the planet Jupiter. So Jupiter's up here in the southern sky. It's really bright. And a few minutes later, it'll be darker still. And then we can see the stars. Can we see them? It starts to warm up. So Elizabeth, would you push down on that you take this, I'm sorry, listen, you're back there. I don't know that you saw that yet. Did I show you that, listen? Along the left edge. Along the left edge of it. You found it. Great. Thanks, Alyssa. Okay, so here we go. Mount Vernon sky on a really super dark night. Like if you live in town, or even like we live just south of Little Mountain, yeah, there's been nights when it's this dark. That's pretty good. It's later spring, and we are losing my favorite constellation, Orion. There's Orion over here. Can you see the 3 bell stars? He's right there. 1, 2, 3. There they are. The 3 belt stars of Orion. Orion is a giant hunter that's up in the sky. And Orion's got a really cool star. And really, compared to other stars, it is cool. It's about 4,000 degrees on the surface. It's not really that cold. But it's a reddish colored star, which tells you it's a red giant, or in this case, it's a red supergiant star that has a really cool name. Its name is Betelgeuse. I'd like you to say that. Say Betelgeuse. There's Betelgeuse right there. Someday Betelgeuse is going to explode as a supernova, the largest explosion in the universe. It's going to be a wait some time, but it's there. Hey, next door to Orion is the Big Dog. The Big Dog constellation's right here. If you want to sound important and knowledgeable, you can say, oh, it's Canis Major, which is the Latin for Big Dog. I like to call it the Stick Dog. Let me show you the Stick Dog. So follow along. It's like connect the dots. So here's the tail of the dog, and there's his spine. Then there's this really bright star named Sirius, like Sirius. His arm is up here. There's not much to see for his head. One front leg goes like this, another front leg like that, and his back leg. I don't know, can you see his big dog? Sort of? Okay, I'm going to show you again. The tail, there's his spine. This super bright star Sirius is like a jewel in his collar. It's a special dog. And then his head's up there, and his front leg, his back leg. So that's the big dog. That also is easier to see like in February, into March, in the middle of April. He's heading towards the horizon. You don't see him so much. But think about this next time you see Sirius. It twinkles like crazy, more than any other star. It goes like blue and turquoise and lavender. It's gorgeous. But it's really far. It's far away, but not that far away. That light, when you see it, has traveled through space for since 2006. It's about 8 years of travel time, 8.5 years of travel time for the light from Sirius to get to us. Oh, if you see Betelgeuse up there, well, Betelgeuse, light left Betelgeuse in the year 1518. And for 497 years has traveled across space at the speed of light, and it gets to Earth tonight. We're talking almost 500 light years of travel time, 500 years away. What else? Oh yeah, Jupiter. I've been watching Jupiter recently. There's a little star cluster up here called the Beehive. If you've got binoculars, you can see it. With your own eyes, it's too faint to see it. With the planetarium, you can. And then the moon, okay, I've got Jupiter. I want to show you Pollux and Castor. Pollux and Castor are the twins. This is Gemini. We're looking at the constellation Gemini right now. This is the constellation Cancer. There's not really much to see there. But next door is the Lion, and the Lion is just about to eat Jupiter. So there's Jupiter, that super bright looking thing up there. Does Jupiter twinkle? No. Twinkle, twinkle, little star. Yeah, you got it. It doesn't twinkle. Here's Leo. There's a backwards question mark right there. There it is. And that you can spot with your own eyes. It's high in the southern sky after sunset this time of year. The heart of the lion is right there. It's Regulus, so like a regal star. The heart of the lion. This is his neck. That's his head. He's about to take a bite out of Jupiter. His spine goes out this way, and he's got his tail underneath him, the front legs folded in. Some of that's hard to see. But it's one of the oldest constellations that we could look back on and say, whoa, the Sumerians in ancient times, the Sumerians actually identified that as a lion. So let's do the lion setting for a long time. If you come to Science Night next year, in April, Jupiter will be right there. And if you do it in 2017, it'll be there. 2018, you get the idea? After 12 years' time, Jupiter will have gone all the way around us, all the way through the stars. It wanders through the stars. Jupiter does that, and the other planets do as well. When you say the word planet, you're almost saying planetes, which is the ancient Greek word for wanderer. Planets wander through the stars. They don't stay in one place. They travel through the stars as the days and weeks go by. Hence, they were called planetes, the wanderers by ancient Greeks. We just call them planets. And that's why. Well, let's find the Big Dipper. Look straight up, almost. Here's the handle of the dipper. There's the cup of the dipper. There it is. Like that. Can you see it? Yeah. This time of year, it's almost straight overhead at sunset. Easy to spot, easier to see outside than it is in here. These two stars in the end are the pointer stars, and they point towards the North Star, which is right there. All right, here's your test. This is how you get out the door later. Is that the brightest star in the sky I'm pointing at? No. Many people think, oh, the North Star is the brightest star in the sky. No, that's Sirius. Sirius. It's Sirius. It's not the North Star. That's the Little Dipper. There's not much of a dipper to see with the Little Dipper. The cup is here, and this is the hand. Okay. I'd like to show you what the sky looks like a little later on. Later on in the night. So the cool thing about the sky is it doesn't just stay there. It's changing all the time. And it's very predictable. The sky moves always with stars rising in the east and stars setting in the west. There goes Orion. And new things appear in the east that weren't visible earlier in the day. And as they come up, it's like a show that just goes on and on and on. If you know what you're looking at, you can always spot something there. Like here comes Saturn. This is at about midnight. Saturn at midnight, maybe closer to 11 o'clock. Saturn will be rising in the constellation of the Scorpion. That's the Scorpion in here. And that is another supergiant star. It's called Antares. If I turn off my red laser pointer, you notice how it looks kind of red? Kind of peachy color? That is any star you see that looks sort of red. Is a red giant or a supergiant. And that's the heart of the Scorpion. Right behind it is the constellation Sagittarius. And because this is the view later on, let's see, this is about the sky in late June at sunset. We're going to go to July at sunset and turn the sky down just a little bit more. And you can see the Milky Way. And I'm going to stop things right about there. So later on, when we get to the end of June, the Milky Way is really prominent. It's high overhead. You gotta wait a long time for it to be this dark. There's the Scorpion. If you can spot Sagittarius, there's a little teapot in the sky. I'll show you the teapot. Here's the handle of the teapot. This is the base. Here's the spout. And then there's the lid. You know the song, I'm a little teapot, short and stout. There you go. Anyway, there's the handle of the teapot, the base. Here's the spout. Right there, above the spout of the teapot, is the center of our galaxy, the Milky Way. There's a black hole at the center of our galaxy with the mass of 3 million suns. And you can't see that black hole, but everything you see in the dome here is orbiting around it, including you and I. Earth is orbiting the sun is orbiting the black hole, the center of our galaxy. Now it's okay, it's 25,000 light years away from us. And we've been orbiting that. Our sun has been orbiting that for about 4.5 billion years. So we're safe, okay? It'll be all right. But there's things there that you can't see with your own eyes. There's energy that's coming from the center of the Milky Way galaxy. In fact, there's energy coming from all over there. We can't see, but certain telescopes can. And that includes the Hubble. So I'm going to turn up the lights just a little bit. And then Alyssa, with your help, let's open up that shutter back there. Push the cardboard back up again. And then you'll see a gray rectangle in space. There it is. You need to go. Okay, the door's gonna open, so close your eyes for a second, brighter. And then we're gonna look at some pictures that the Hubble took. So you need to close your eyes again, because the first picture is pretty bright. Right? So everybody squint for a second. Here's the first picture, and there it is. It's bright because that's Earth. Earth from space is really bright when you look at it. It reflects light really well on the sunny side. And there's the Hubble orbiting over the Earth, 16,800 miles an hour, hour and a half to go around the Earth once. It's been doing that for 25 years. When it was first launched, its mirror had a flaw, and that flaw in the mirror made for fuzzy images. This is the same galaxy M100. After a repair mission, astronauts went to Hubble 5 times to fix it. The vision was much better. It was like they put eyeglasses on Hubble and fixed what could have been a huge disaster. Amazing device. So 5 different missions went up to repair the Hubble on space shuttle missions. No more. There's no more space shuttle. And so when Hubble breaks down, that's going to be the end. Hopefully it'll keep going for until 2020. That's what they expect. It's still working wonderfully now, better than ever. These are just a few of the images that it's taken. Remember, Hubble is like a time machine. Looking at light from planets, we're talking minutes. Or light from Pluto, it's 5.5 hours for light from Pluto to reach Earth. Stars, well, hundreds of years, or thousands of years. Galaxies, on the other hand, millions of years or billions of years for the light to travel across space. Hubble can see it all. Jupiter has changed since Hubble was launched. The red spot, Galileo saw this in 1610 with his little tiny telescope. Look what's happened to it in 19 years' time. It's getting smaller. An instrument like this sometimes uncovers more questions than it does answers. Nobody knows why Hubble's doing that, or why the Jupiter's doing it. The spot's getting smaller. Europa, one of the moons of Jupiter, Galileo saw it. We know now that it's water, frozen water, and maybe has liquid water underneath it, which would be a totally amazing thing. Because if there's liquid water, maybe there could be living things in that frozen water, under the frozen water. Okay, Jupiter can be seen in other wavelengths than just visible light. Ultraviolet vision, you can see auroras, glowing clouds of gas above the upper atmosphere. It looks like that. Saturn has aurora too. I love these 3 pictures. The tan is the visible light color of Saturn. Using ultraviolet light, you can see those glowing clouds above. It's beautiful. Pluto, July 14th of this year, the New Horizons spacecraft reaches Pluto. It's been traveling from Earth for 9 years. And July 14th it gets here. Hubble was used to take pictures to look for other things that could be explored. So here are all these pictures in that region. Hubble took all those pictures and spotted some other objects. You can see that one right there. So the New Horizons spacecraft may be looking at that object. They call it PT-1. Just so you know, Pluto is pretty small compared to the Earth, or Earth's moon. It's quite a destination. July 14th, we'll hear all about it. So beyond the solar system, looking out, here is a cloud of gas called the Carina Nebula. Spectacular, glowing cloud, mainly hydrogen, but there's dark clouds where there are new stars. Right there, new stars inside that cloud that are lighting the cloud up. You ever seen this picture before? It was one of the more famous ones, Hubble Space Telescope. This was released in 1995. called Pillars of Creation. It's a part of what's known as the Eagle Nebula. So that's the 95 view. Look at the one that was just released. Same place, using new instruments, reprocessed data. 1995, 2015. A new camera that gets a much wider field of view. Dark clouds. Again, there are brand new stars in there. Hubble can see in infrared as well. Using infrared energy, the light can be seen coming from objects inside dust clouds like this. This is the same object. I'm going to flip back. And flip it up. All right? We can't see infrared with our eyes, but Hubble can. And with that, it can see deep into clouds and see, for example, the star right there. It's just barely visible when you look at the cloud, but in infrared, the light of the star is obvious there. Pretty cool, isn't it? This is the Horsehead Nebula. Visible light, it looks like this. It's part of the nebula in the constellation of Orion. A dark nebula, again, brand new stars inside it. Here's a zoom in on that part. The Horsehead. It's not look like a horse head. I like to call it the seahorse head. Okay, but look at it using Hubble's infrared vision. It looks like this. So I'm going to flip back again. Visible light, infrared. And you especially pay attention to this bright star right there. You can see it's blowing away the cloud around it. There's a star there, just barely see it, but using infrared, it's glowing bright. Astronomers learn so much about stars and nebulas by using vision like this. In the Orion Nebula, you can see brand new stars with solar systems forming around. That's a star that's way down inside that little square. And inside this, another star way down inside that little blob. Hubble's seen planets orbiting other stars using infrared. And in this case, you can see that planet is gone from 2004 up in 8 years' time. It's orbiting a star called Ultrasound. So many beautiful things. We've just grown to take it for granted. A dying star. Another dying star. A star that exploded. People on Earth could see this one with their own eyes in the year 1054, the Crab supernova remnant. At the center of it is a neutron star. Sometimes stars are massive enough when they explode to leave black holes. This one is a neutron star. Another supernova remnant, very faint. It's a cloud of gas that's puffing out into space. I'm going to zoom past a couple of these pictures because there's one I want to show you. This is light that's traveled for 37 million years across space before it reached Hubble. The Whirlpool Galaxy, or Sombrero Galaxy. Again, millions of years ago. That's what it looked like. Because it takes like millions of years to get to this. The crash of two giant galaxies. Here they are, a bigger view, and up close they look like that through the eyes of light. I'm going to zip to this picture. This picture is what the universe used to look like. Only now we're talking billions of years. In a region of the sky as big as that square compared to the moon, Hubble stared for hours and hours and hours, collected all this light. This is a view of 10,000 galaxies in that square just that big. The red objects in here, over here, those are galaxies that are about 13 billion years of light travel time away. Light traveled for 13 billion years and then it reached the Hubble. So this is what the universe used to look like billions of years ago. The light is just getting to us now. So when you look out to space, you're looking back in time. Telescopes are what it takes to do that. Hubble's nearing the end of its life. It's been amazing. An 8-foot mirror. 2.4 meters. Its replacement is the James Webb Space Telescope, which uses several mirrors hooked together for a total size of 6.5 meters. So it's much bigger. But it's going to see an infrared lesion rather than just visible light. And it won't be launched until 2018. Things keep going. Hopefully, it'll go. If you at all are interested in exploring more stuff about Hubble, just Google Hubble 25. There's a lot of cool stuff. Videos and flybys and zoom-ins. It's really amazing. I need to turn the lights on. I think I hear some restless voices outside. Folks that are ready to come in. Wow.